This is our first screencast for Chapter 15, Introduction to Electricity in general, specifically electrostatics. And if you think about electricity, obviously something that's very significant is if you're going to have a technological civilization with all of the advantages and blessings that it can bring, you need inexpensive source of energy, and electricity is that kind of energy that can do that. Try to imagine any culture without electricity. And they, of course, mentioned there go our phones and television and household appliances. Modern medicine depends upon that. Transportation, communication, scientific research goes on and on and on. We need lots of electricity, and it needs to be inexpensive, especially for nations that are trying to reach a level of development where they can provide for their people and lift people out of poverty. There's a lot of politics we can talk about there, but that's not our place at the moment. Another idea here is that with the discovery and harnessing of these electric forces and fields, this now enables us to begin to investigate the outer space, our solar system, everything beyond. Again, the implication seems to be that not only did God provide for human flourishing by creating the phenomenon called electricity, that is made possible by the way in which he designed the universe, but also put into our universe many, many sources of energy that can produce that electricity. And one of his purposes, besides to promote human flourishing, is for all of us to begin to investigate outer space, to ask the big questions. Where are we in the overall scope of the cosmos? Why are we here? Are we significant? Are we important? And of course, depending upon your worldview, you'll have very different answers to that question. The biblical worldview, of course, is that when we look at the incredible design of the universe and the fine-tuning of the universe and everything that has to be just right for the planet that we live on, to have all of the kinds of conditions and constants and restraints and resources that it needs to have for there to be not just life, but the kind of life that we would call human life that can ask the big questions. One conclusion, the biblical conclusion, is we are very special in God's sight. We are meant to be here. We are designed for a purpose. Not only is the universe something that has purpose, but therefore so do we. Not only is there meaning in the universe, but that means we have meaning as well. Now, this study of electricity goes back at least to 700 years before the time of Christ. And one of the things that was noticed early on is if you take some of that pine sap that is hardened, especially the pine sap that occasionally would entrap an insect or bug of some type, amber, and you were to rub that on something like wool, you could create what we now know to be a static charge. And they observed that phenomenon and probably were able to move pieces of dried grass clippings or maybe pieces of parchment or something like that around and noted and began to study that. So we're going to begin by looking at charging by friction, and then we're going to discuss Coulomb's law in this first screencast. So, you're very familiar with static electricity, I would imagine. And back when I used to have hair, you could use a plastic comb and take it through your hair, and the plastic comb could become charged, and you could make small pieces of paper or even styrofoam move around, dance about, or even cause your hair to stand on end if two pieces of hair happen to have the same charge. We also know that if you were to take a balloon and rub it on your clothing or your hair, that you could take that balloon, hold it up next to a wall, and it would, quote, stick, unquote, to the wall. The idea, of course, is the balloon has acquired a negative charge by electrons being rubbed off of you, which we would now understand, they wouldn't initially when they did this, that repels electrons from the portion of the wall that you hold the balloon next to, making it a positively charged region, and so your negatively charged balloon could be attracted to the positively charged region on the wall, and it would stick there, so to speak, and depending upon humidity and so forth, it could stay there for some amount of time. Maybe you've walked across a carpet and picked up a static charge. Maybe you've moved around in flannel pajamas under the sheets or under a blanket and picked up a static charge. Maybe you slid across a car seat and touched something metal as you were getting out. These are all examples of picking up a static charge. You have to be sympathetic for those people that used to man the toll booths at tollways, and they had to very quickly realize you had to discharge cars driving down the highway as they picked up a static charge. Discharge them before somebody with metal coins tried to hand them to the poor attendant and shocked the attendant time and time again. We also know that this is more likely to take place on dry days, because when you have moisture in the air, the electrical charge is more likely to leak away. As far as a modern day understanding of electricity is concerned, Benjamin Franklin played a big role in that. He believed in God. He was probably what we might call a deist. And in any case, a very significant contribution was simply recognizing two kinds of charges, positive and negative. And of course, he was sort of a polymath, as you can read about him, and had his hands in all kinds of things, including politics and diplomacy. Now, in this particular picture, you see what could happen if you take a glass rod and rub it on something. It often will lose its electrons, acquiring a positive charge. And then if you hold it next to a rubber rod, the electrons will be attracted to that end of the rubber rod that's closest to the positively charged glass rod, and the two rods would begin to move towards each other. Whereas in this picture over here, if you charged up a rubber rod, it acquires electrons, so it becomes negatively charged, and that's going to repel a negatively charged rubber rod on the other side. And right off the bat, you can see that like charges attract and opposite charges repel. Fundamental rule, which is mentioned right here. Now, it all goes down to a study of physics at the atomic level, something that you learned about in chemistry. And you learned that atoms are basically made out of positive charges, neutral charges, and negative charges. The positive and neutral charges, protons and neutrons, are located in the nucleus. Some people have trouble remembering which is which. You could think of pro as being positive about something, neutral from the word neutral, zero, and then of course electrons are negative because they're the only one that's left. Because they are not stuck in the nucleus in a systematically designed and arranged fashion, which we don't entirely understand the nucleus. The electrons we know a little bit more about, and quantum chemistry helps us to understand an awful lot about their location and position and movement outside of the nucleus, but they are very, very mobile, and therefore they are the ones that are going to be rubbed on or rubbed off when there is friction. If you had a gram of matter, you would have approximately 10 to the 23rd positively charged protons and 10 to the 23rd negatively charged electrons, giving you a near zero charge. And you might recognize that number as coming from Avogadro's number, which was this number right here, which is the number of particles in a mole of something. And that, of course, that's a very, very large number. And so it's the electrons that are mobile, it's the electrons that are moving around, creating things that have positive and negative charges. We also know now that charge is conserved. Charge is neither created nor destroyed. You don't expect magic anymore when you reject a worldview of polytheism or a worldview of animism or magic. But when you embrace a worldview or benefit from a worldview where if there is just one God, there is only going to be one set of rules, and if that God reveals himself as being a God of order, then you expect there to be order in creation. You would expect creation to reflect the Creator. That God is a lawgiver, so you would expect there to be laws in the creation, and therefore you would not expect anything to come out of nowhere or disappear somewhere unaccounted for. And so we talk about the rules of conservation, and here's one: electric charge is always conserved. If something loses electrons, it's got to lose it to something else that's going to gain those electrons, and vice versa. Another thing we should point out is that the electrical charge is quantized. That means it comes in discrete chunks. It's not like an analog scale, but you either have one chunk or two chunks or three chunks, or you're missing one or two or three, but you can't have half or part of a chunk of charge. And that smallest chunk of charge is called the electron. And so when you gain or lose electrons, it's going to be some multiple of a whole number. It's never going to be a fraction. And thanks to the work of a guy named Millikan, and I want to double check that I didn't miss a discussion of Millikan. Oh, there he is, Robert Millikan. Very, very interesting individual. This is last century, 20th century, first half of the 20th century. He actually died a year after I was born, just in case you think I'm really old. And he was a very devout Christian, was demonstrated the fruits of the Spirit throughout his entire life. He was a Nobel Prize winner in 1923, which is pretty young age, relatively young. He had 25 honorary doctorates. He was the founder of Caltech, which is the West Coast competing school of the East Coast MIT in Boston, where my dad graduated in electrical engineering. He was very critical of the broader macroevolutionary theory as being a theory of everything, and he thought that people during this time were being overly confident in this theory as being a theory that pretty much was not going to be changed or modified or maybe even rejected in the years to come. He did advocate humility and actually was very much a promoter of ethics overall, especially on the part of scientists. He even used some of the language that I've been using all along. He talked about the great architect, the Creator God. Also on this page, by the way, it's a little reminder that when it comes to quantum mechanics and charge, we can go all the way to the level of quarks, which perhaps make up some of these subatomic particles like protons and neutrons. Now, continuing with Millikan, his very famous Millikan oil drop experiment, which we'll talk about towards the end of the chapter, helped us to understand the fundamental charge called an electron and the magnitude of that charge, which was a pretty phenomenal accomplishment considering the limitations they had in terms of their equipment and the absence of any computing capability with our modern day computers. Two words you probably already know. A conductor is going to be something that conducts electrical charge. Incidentally, good conductors also conduct heat as well, as you recall way back in some earlier chapters last semester, 9, 10, 11, 12. And then you have materials that are not good conductors of electricity, and the opposite of a conductor would be an insulator. Metals, for example, make very, very good conductors of electricity. We're trying to find other materials, such as the pure carbon in the form of graphene might be a good conductor if we can figure out how to harness that Nobel Prize-winning discovery of about a decade ago or so. Glass and rubber are good insulators. Metals with their mobile electrons, their delocalized electrons. When you think of metals like copper, and aluminum and silver, their electrons are delocalized. Remember that phrase? Because you have this matrix, this geometrical array of the positive metal nuclei in a crystalline structure, swimming in a veritable sea of electrons, and the word we use to describe all those electrons is they are delocalized instead of being locked, so to speak, in their respective orbitals with the metal nucleus at the center. And because these electrons are delocalized, they can transport a charge and they can also transport heat. Remember, in order to conduct electricity, you need mobile charged particles, MPCP. And those mobile charged particles in metals are electrons, but in a salt solution, they would be ions, and in a liquid salt, they would be ions. Now, we have good conductors, and we have bad conductors, or we could say non-conductors, and as usual, we make these nice categories, only to find out there are some elements that don't quite fit either category, and we call them semiconductors. God is very good, and it is frequent in his creation for us to find these exceptions to our categories, which turned out to be extremely important. A semiconducting material, for example, would be silicon. And of course, that's fundamental in our modern computer technology. All right, charging by conduction and charging by induction. Whenever you think of the word conduction, you need to think of the word contact. Just like with heat, when you charge by conduction, you're actually going to touch something with a charged object, and it's either going to acquire electrons from the thing that you touch or leave behind electrons from the thing that you touch, and therefore it becomes charged. That's by conduction. Induction is a way of causing something to become charged without physically touching it. And a very important word that we're going to be using here in a minute is the word grounded, which is the way in which we enable an excess of electrons to return to the ground. In a sense, the Earth is like our electron sink, where all excess electrons eventually go into. Think of lightning. Lightning is going to be huge masses of an electrical charge that might go from cloud to earth, or earth to cloud, or from one cloud to another cloud, or from part of one cloud to the opposite part of that same cloud. But when it goes down into the ground, we say it is grounded, and we want our electrical appliances to be grounded. You might have a lightning rod on the corner of your house connected to a stout wire that goes down into the ground. If you go down in your basement, if you have one, you might find a very, very thick copper wire that's clamped to a copper pipe maybe that goes down into the ground. So any static electricity that is picked up is going to go down into the ground. It is grounded. Later on, you're going to see the symbol for grounding. So let's take a look at how induction can take place. And I'm going to move this over to the other side. And so here we are charging up a rod by rubbing it on a piece of silk. This is a glass rod on silk. And the electrons are transferred from the glass to the silk, just the opposite of what happens when you take a piece of black plastic and rub it on fur. And then when you hold that charged rod up next to this metal sphere, you're not touching it yet. You can see the little space there. It pushes all the electrons away, leaving behind a positively charged part of the sphere. Now, of course, if you touch the object, this would be conduction. Now those electrons are going to be left behind. The excess electrons from here are going to be left behind over here. And now when you remove the rod, you're going to have an excess of electrons down here, evenly distributed throughout the rod, and you've charged up the metal sphere by conduction. Now let's look at what happens by induction. Let's move this over here. When we have induction, this case we're going to take our charged rod right there. It's negatively charged again. Hold it up next to our sphere. It's going to cause the negative electrons to be repelled and move away. And then what we do is we take a wire and we ground it. Look at the symbol for grounding, the little lines that get shorter and shorter. If you see that in electrical diagram, it means this is a place where the electrons can go back into the earth. And so your excess of electrons that you gave to the sphere go down the drain, so to speak. And then when you begin to remove your rod away so you can't see it anymore, now you'll notice that you have more positive charges than negative charges because you've just dumped some into the earth, and now you have a positively charged sphere without ever touching it, other than touching it with a grounding wire. Another thing you should point out is that you can get polarization. Polarization is when you have something that is polar. In chemistry, you learned about the polar water molecule. You have the positive part where the hydrogen nuclei are, and then you got the negative part where the unshared pairs of electrons are in the oxygen atom. So you have a negative pole and a positive pole for the polar water molecule. We talk about the Earth being polar with the North Pole and the South Pole, and there's our equator. So polarization is going to be when you have one part of your object is negatively charged and the other part of your object is going to be positively charged. And you create polarity there. We're going to get into that a lot more when we get to capacitors in the next chapter. All right, Coulomb's law. Coulomb's law, made by Charles Coulomb. Now we're talking about the 18th century. French individual, Roman Catholic, at least at birth. We don't know much about his faith or whether he practiced it or not. A lot of times, whatever extant literature and writings we have on people, for whatever reason, they don't talk about anything but their particular scientific work. And you could say the same thing about historians and politicians and so forth. Some people are outspoken about what they believe or don't believe, and other people aren't. I don't know where he stood. Probably if he was Roman Catholic, he may have certainly embraced some of the main principles of Catholicism, which would include at least a tacit trusting in the Bible and God, and the belief that God, Jesus is God's Son. Can't say from that whether he was a Christian or not. But we're going to intuitively derive Coulomb's law here, which is going to be summarized in these statements right there. So if we come up to the next page, you can see Coulomb's law, but if we were to think about having two charged objects, let's say one of our charged objects we're going to designate as Q1, where the letter Q, sometimes it's capital Q, represents the quantity of charge. Now don't confuse this with Q and lowercase q, which sometimes in earlier chapters stood for heat, the quantity of heat. Here we're talking about the quantity of charge. And you would know that the force of attraction between two charged objects, and I'm going to start this over again. The force of attraction or repulsion between two charged objects would depend upon the magnitude of one of those charges. The bigger that charge, the greater we would expect the force of attraction or repulsion to be. And the same would hold true for the other charged particle. And if we did a little bit of thinking, it would be logical, and it would be borne out by experiment, that the force of interaction between the two charged particles would be inversely proportional to the distance between them. That if you took your two charged particles, and let's say that they were this far apart, and then you move them this far apart, you expect that the attraction or repulsion between them would be much less. Just the same way that we saw it in gravity and the force of gravitational attraction. This turns out to be an inverse square law if we had the ability to do some preliminary experiments, and that means you double the distance between the two charged particles and the force of interaction would be 2 squared or 4 times less. Triple the distance, 9 times less, and so forth. Then when you put all of this together, you get an equation that looks just like Newton's universal law of gravity, and that's this. We need a proportionality constant, which we'll talk about in a minute, and there's Coulomb's law, which of course you see right there. This implies, by the similarity of the structure of of Coulomb's law and Newton's law, where we use G as our proportionality constant, m1, m2 divided by the distance between them squared, that there's some relationship, some similarity between electrostatics and gravity. We certainly suspect that. We all think, or I should say most scientists think, that at some point, maybe at the moment that the universe came into existence, all of the forces were unified. Very quickly, the gravitational force became very different from the electrostatic force, the weak nuclear force, and the strong nuclear force. So we have yet to reconcile the gravitational force with the others very well. Now let's talk about this value of K a little bit. This Coulomb's constant here, this charge constant, we know to, I think, at least 12 places now. It is finely tuned. It has to be exactly what it is. If it was too great, all your atoms and the electrons would all collapse in on the protons. If it was too weak, all the electrons would easily be lost, and you would have very, very great difficulty having any kind of stable atoms at all, and therefore no stable elements either, for that matter. So it's finely tuned, and many people have remarked that it's so finely tuned, it doesn't look like an accident or chance, but something that was designed, something that was intentional, something that was instilled at the very get-go, because the purpose was to have a universe such as we have now. And it's one of those arguments for intelligent design, which is often abbreviated ID, intelligent design. Something that I subscribe to and I teach about all the time, and hopefully you've heard me. I'm doing it right now. The value of K actually equals the reciprocal of 1 over 4 pi times epsilon naught. And epsilon is called the vacuum permittivity, which is sort of like the limit or the permitted maximum electrical field density that you can have in a pure vacuum. That'll be talked about a little bit more later. It comes up again. So that's that value of K. Notice how this irrational number, which we know to over 1 trillion places now, believe it or not, pi shows up so many places. It's funny to think about something that is irrational by man's definition. Our definition of numbers is extremely integral to and found in many places in creation. So moving along, here it is to 5 significant digits. And if you only needed 1 significant digit, it's pretty close to 9 times 10 to the 9th, which is an easy number to kind of try to remember. You might remember that the gravitational constant was 6.67 times 10 to the minus 11th. Look how different. Extremely small, extremely big, with an order of magnitude that quite large between the two, at least 10 to the 20th power in difference. You might also know, of course, that as far as we know, there is no negative or anti-gravitational force of repulsion. In electrostatics, you've got repulsion and attraction. However, we are investigating this, and you'll come across terms like hypercharge or anti-gravity, things like that. So maybe there is a equal and opposite gravitational something, we wouldn't call it gravity, but an anti-gravitational force of repulsion. That part of that becomes a possibility, or it factors into the theoretical thinking of people as they investigate dark energy and dark matter. And when we come down here and talk about these delocalized or free electrons in a cubic centimeter of copper, once again, there's that number from Avogadro, about 10 to the 23rd. Now, that's a huge amount of charge, so most of the time in electrostatics, we'll be talking about microcoulombs. And there you have the lowercase Greek m, micro. And that's a symbol you better remember. It pops up often in physics. Because this is a force, whether attraction or repulsion, it's therefore a vector quantity. We haven't had vectors in a while, so we're going to do a little bit of review of that. And they do obey Newton's third law, even though these are not laws of motion per se. Newton's third law says for every action there's an equal and opposite reaction. So if you come down here and take this quick quiz, you should be able to rapidly figure out which one of these three answers is the correct one. And I would pause if I were you at this point, force yourself to make a decision. And now, if you're listening again, the correct answer for every force there's an equal and opposite force, there it is. Both have the magnitude F, and it's the opposite. Down here you can see that electrons and protons have equal and opposite, have the same mass. Protons and neutrons have almost the same mass. That's not to 3 sig digs, yes, but not to more sig digs. But you can see that the electron and proton have the same charge, but opposite there. Remember, the neutron actually has a mass approximately equal to a proton plus an electron. And now we're going to do a couple math problems to investigate these forces. So this is a very interesting problem. It says, consider a hydrogen atom which has 1 proton, no neutrons, and 1 electron. And so we're talking about protium, which is the name of the hydrogen isotope, H1. Okay? So it's H1. That number up there is the sum of the protons and the neutrons, which is 1. This is the charge number, the mass number, the proton number, which is a 1. And it's an atom, so its electrical charge is 0. And because it's just an atom and not a molecule, we don't have any number down there at all, as opposed to hydrogen gas, which is always diatomic. Now, when we use Coulomb's law right here, and we put in an electron and a proton, we put that in there because it's the charge of the proton and the electron. They each have the same charge, so in a sense we're squaring it. There's the distance as estimated between the two particles. And when we plug in the math with the value of K, we get 8.2 times 10 to the minus 8th, or about 0.8 billionth of a Newton. Now, technically speaking, we should say that because this electron is negative and the proton is positive, this is a force of attraction, and so technically this value would come out to be negative. And when we have positive times negative forces of attraction they come together. Now, and I'm going to erase the positive sign so it doesn't confuse you. If we had an electron and an electron, or a proton and a proton, negative times negative gives me positive, positive times positive gives me positive, our answer would come out positive, and that would imply a force of repulsion because like charges repel. Now we come down here, and now we're going to do the Newton's universal law of gravity. We're going to plug in the mass of an electron, and then here we're going to plug in the mass of my proton, about 2,000 times, or 1,836 times greater. Same distance between the two, And look how minuscule that gravitational force of attraction is between the electron and the proton. And if we find the difference between the two, divide this number by this number, we get this astronomically small number, or large number, I should say, 2.3 times 10 to the 39th, which shows how much greater is the electrostatic force compared to the gravitational force. Now, we can take this electrostatic force of attraction and put it down here and divide it by the mass of my proton, and therefore I can get the mass of the electron, and I can get the acceleration of my electron. And that is a gigantic acceleration of 9 times 10 to the 22 meters per second squared. You could say that motion would be practically instantaneous. And it would appear to us, because we wouldn't have any equipment that can measure anything that fast. And then finally, if we want to use Newton's second law and the gravitational force, we can plug this into to find the acceleration here. And in this case, the acceleration using gravity. Here's my gravitational force of attraction from the previous problem. And now we took the put the mass of an electron there just like before. And you can see that this speed is 10 to the minus 17th meters per second. A whole lot slower than before. Now we should mention that you can have multiple particles interacting with each other. And in order to figure that out, we can use the principle of superposition. You had the principle of superposition, or maybe you will get it in optics, when you add up the amplitudes of multiple waves in a medium, transverse waves, and in order to find the resultant wave, this is something that similar type use of the word, but it has a different meaning and application here. So imagine we've got 3 spheres, a positive sphere there and a positive sphere there, and the question is, where should we put the negative sphere in between? Where will it end up so that it'll be in equilibrium? It'll be pulled from the left and from the right equally, so it will not accelerate at all. Where will the two forces equal each other? And so as we attack this problem, we're going to use Newton's Coulomb's law, twice. We're going to use it for the interaction between particle 1 and particle 3, designated as F13, and that's going to be right here. And then we're going to use the same law again for F23 between particle number 2 and particle number 3, and that's used right there. And we're going to plug in the magnitude of my charges, which were given to me in the problem. There's Q2, there's Q1. We're going to plug that in here and here. Q3, we don't know what it is. And if the distance between the two particles is 2 meters, then the distance between the particle that we're trying to locate and put at equilibrium and charge 2, we'll call that x, which makes the other side 2 minus x, which is where we get the denominator. Now don't forget to square it. Common mistake. Don't forget to square the distance. It's an inverse square law. And when we solve this equation, it's a little bit of algebra, and we work our way down. We can cancel out k's down here, cancel out the k. We can cancel out the million part, but we still end up with a quadratic equation. And so when we use our quadratic equation, or we plug it into the quadratic equation that might be preloaded in your calculator, negative b plus or minus b squared minus 4ac over 2a, if I remember correctly, you would get two numbers. One would be a nonsensical number, a negative distance, and you would get this distance. And that would tell you how far away the middle particle will be when it's in equilibrium between the two particles. I should say how far away from the particle on the left. And now we can move into 2 dimensions very quickly. When we move into 2 dimensions, again, we're going to have a force of repulsion between here and here, and that means the particle is going to want to move this way because of Q1. but Q3 is going to want to be attracted this way because it'd be attracted to a negatively charged particle, Q2. Now, when we go to add these two vectors together, the first thing we're going to do is componentize. We're going to take the vector acting an angle and find its x component and its y component. And once we know its two components, then what we're going to do is we are going to add these two components together, which of course one is going to partially cancel out the other, and that'll give us our net component in the x direction, and our net component in the y direction, of course, since there is only one vector, is going to be F13, acting straight up. So when we go to do our work, here we find the magnitude of the force of attraction between F2 and F3, and remember, one was positive, one was negative. Here's Q2 and here's Q3. And so that's going to be moving in the y direction, or the negative direction, indicated by that negative sign. And of course, it has no motion in the y direction. Then when we look at the ones between the two vectors, the two particles that are both positive, acting in this way, this is going to be a repulsion, which is going to send the particle in that direction. And so we can calculate that right there by plugging the numbers in. And then we componentize this vector right here. We're going to componentize it, and we get that value and that value. Then when we go to create our triangle, our net vector in the x direction, 3.02 times 10 to the minus 9th, or nanonewtons, 6.48 upward nanonewtons. And we're just going to be finding the diagonal, the resultant of those two, and we also have to find the angle. We can find the resultant using the Pythagorean theorem, and we can also find the angle.